This is video 5.1. It deals with wave measurement and wave behavior. So waves are always caused by vibrations of some kinds or oscillations, and we have the idea of frequency, how many vibrations or oscillations or cycles per second, how far the movement is of those vibrations, how long it takes for one. We've got a couple of different equations that model that for us, and we have a couple of terms. We should always remember that energy is transferred and not matter. That's the essence of a wave. Then we have another section here, absorption, the idea that the energy is being absorbed, and that's what hearing is. Then we have reflection, so a change in direction or a bouncing off of waves, and how that's useful to us in ultrasound and in sonar. Then finally we look at propagation, or the final section, propagation. A bit of a posh word there, but it just means, how does it move? What are the different ways that they move forward? And we have two key types, longitudinal and transverse. How do we measure that speed, and why should that speed change? So here we then have a representation of a wave. So this is a transverse wave, and we can see it moving from left to right. Now the wavelength kind of describes itself. It's a peak to peak distance we're showing here. It could be trough to trough as well, or any other points of similar phase. And the amplitude is the height of the wave. Now it's from this middle position, the undisturbed position. It's not from the top to the bottom, as you might expect. And examiners love to ask you that. So here we've got then time period. So this is the length of time it takes one wave to pass a point. You can pick any point here. So here we go. It takes about 4 seconds for this to pass a particular point. Then we have frequency, so that's the inverse, or 1 over the time period. So 1 over 4 is a quarter. So we have a quarter of a wave per second passing any particular point. So here's a summary of those key ideas, wave speed as well. So we've got our descriptions there, and we have two formulas. The one we've already alluded to, frequency is 1 over time period, but then this one is a key one which we'll look at in the next slide, which is that velocity is frequency times wavelength. So let's have a look at why this makes sense. So if we think of a train, we can think of carriages passing us on a platform. We know, if we know the length of a carriage, and we know there's 3 per second, we could work out the speed of the train. Even if we weren't there when the train started to come through, we could still work out the speed. And that's exactly what a wave is. It's a series of cycles, so it behaves very much like a train in that respect. So here we are, we've got frequency. Remember, we're adjusting for the K to make it 3000. We're adjusting for the centimeters to make it 0.1 meters. So we're working hertz, which is waves per second, and meters, and we get the speed of sound, which is typically about 300 meters per second. Moving on then, we've already alluded to this, the difference between transverse and longitudinal. So here we have our transverse wave again. Now, the thing they have in common is that in this case they're both moving to the right. The energy of the wave is, or that could contain some useful information, is moving to the right in both cases. But the particles themselves are vibrating in different orientations. So here, the transverse, they're going up and down. Here in the longitudinal, they're moving parallel to the direction of travel. So it's quite difficult to state in a concise and short way, but the essence of it is, in a transverse wave, the particles are moving at 90 degrees to the direction of travel, and a longitudinal wave, they're traveling parallel to the direction of travel. Here we've got some examples of the two types. So sound is a key example of longitudinal wave. A slinky can also be made to model this. Earthquakes have both kinds, which we'll see in another video, primary and secondary. A rope, you can flick it up, and that's pretty much what that looks like. Water waves, and the key one for us in the next section is electromagnetic waves. So let's slightly return to this formula. So this is the transmission of sound, and sound waves actually speed up in a denser materials. This is the exact opposite of what light does. You'll see that in the next video. But you can see here, so this might be glass, this might be air, and the sound waves, the compression waves, will speed up. So remember, this is not matter moving, but this is the crest of the wave, or the high pressure point moving along. So in terms of the formula, what does that mean? Well, if we rearrange this, we know that frequency is velocity over lambda. This is the wavelength. This symbol means wavelength. So frequency can't change. As the title of this slide says, you can't make or destroy wavefronts at a boundary. So it makes sense that doesn't change. So if the velocity is increasing, then the wavelength must also be increasing, and hopefully you can see both of those in this animation. Bigger peak-to-peak distance and a higher velocity. So 3 behaviours are summarised here: reflection, transmission, and absorption. So reflection is an echo in the context of sound, and you'll see them bouncing back here in a second. Transmission, we've just seen in the previous slide. It just means it's transmitting it, it's allowing the wave through. And finally, absorption means that it's not allowing it through, and in a very short distance it's turning the energy into heat, and it's not allowing that wave to pass through. So uses of waves, a key one is ultrasound. It sends very high frequency sound, so above human hearing. That's what ultra means, above 20,000 hertz, but millions of hertz in many cases. It reflects off the unborn baby is the key example, but there are other examples, and it creates this kind of image. And the computer is working out, it knows the speed of sound in human tissues, in water, and it can work out from the time of the echo how far away the surface from which it reflected off is, and it creates an image as a result of that. So it's a very low risk way, because it's just sound, it's in no danger to the mother or the child, and it produces some very, very useful images to check on the health of the child. But as I said, it's completely safe. It doesn't produce a very high resolution image, but it's still a very, very useful one. We have sonar, which is in many respects similar in that we're sending off a sound wave and it's bouncing off something, and we're using the time to work out the distance. Obviously the context is very different, but the principle's the same. So here we've got quite a sophisticated model in the background, and we can see this sunken wreck being discovered here using here we've got sound being used to transmit information. So we've got the various parts of the ear that are transmitting this energy, and we can make sense of this. And these tiny hairs we have in this part of the inner ear called the cochlea will vibrate, and certain ones only vibrate at certain frequencies, so we can make sense of the incoming wave. The more violently they vibrate, the louder something is, and obviously the more frequently they vibrate, the higher the pitch is, and we can make sense what we're hearing. Now, unfortunately, with age, these hairs do die and they degrade. They aren't replaced as well. Particularly in the higher frequencies, you can see here with age there's a significant drop-off with this sensitivity. So finally, almost finally, the speed. One way we can do this is we can create some sound and some light at the same time. Light travels about 1,000,000 times quicker, and if we start on the smoke and then stop on the sound, we get a pretty good estimate of the time it takes for sound to bridge this distance, and from that we can calculate speed. Finally then, the idea that a wave, or reiterating the idea that a wave doesn't transfer matter, so the water is not moving along, it's moving up and down, it's the wave that's moving along. If the water was moving along, the duck would move along with it. So the duck's not doing that, it's just going up and down, which tells us it's energy being transferred, not matter.